to take any gradient vector field of any existing discrete Morse function and number it while maintaining the critical and non-critical values and maintaining any homological sequence of your desire. Now, when I say graph, many of you are instantly going to think of a Cartesian graph, an X and Y graph, but in this particular case, I'm actually referring to a graph that would look more like that, which is a collection of dots and lines, or as they're more formally known, vertices rather, and edges. And a discrete Morse function is a graph like the ones I just showed you, comprised of vertices and edges, and each individual edge and vertice is numbered. And for a discrete Morse function, each individual edge needs to be numbered so that it has a value higher to any instant, by instant I mean connected, any connected vertice with at most one exception. For example, this is a discrete Morse function, and you'll notice that each vertice is only connected to edges that have higher values with at most one exception. A critical value is a value that does not break that rule, and therefore there are no exceptions. That would be an example of a discrete Morse function with the critical values being highlighted in red and the non-critical values being left as they were. And a gradient vector field is a much cleaner way of labeling critical and non-critical values, with all the non-critical edges having arrows on them pointing away from the incident non-critical vertices. And lastly, a homological sequence basically outlines what are the critical values in a graph and a discrete Morse function, which are significant because at each critical point, the Betty number changes. The Betty number is another way of saying the number of components that a graph is broken into. For example, if I was to assemble this graph, bringing in components one at a time based on what their numbers were, we'd start with 0, which is the first critical value, and you'd have that first vertice right there. And then I could bring in 1, and then I could bring in 2, and as I brought in 1 and 2, the graph would still only have one component, until I got to 3, where now there is a second component, and then I could bring in 4, and now there's a third component. And then I could bring in 5, which bridges 3 and 4, so now we're back to 2 components, and so on and so forth. So basically, the number of components that the graph is broken into changes with each critical value, which is why the homological sequence is significant. Now, for the algorithm itself, we wanted to come up with a clean, easy, practical way to say, here's a gradient vector field, here's a homological sequence, we want to number them so the critical values are maintained, and it keeps its status as a discrete Morse function. So we started, it's a 5-step process that loops around and takes in the user input. It's much like a Java file that takes in your input based on whether you want to increase or decrease the homological sequence at a certain point. However, you may realize that the first 2 numbers of any homological sequence have to be 1 and 2, at least if it has more than one number in the homological sequence. The homological sequence has to have an odd number. So the first step is very simple. You initiate some random variable, let's say n equal to 1. And then step 2, or step 1, whatever you prefer to call it, basically you pick 2 critical vertices that have exactly 1 critical edge between them on any random path from one to the other along the discrete Morse function. And you would label them as n and n plus 1, in this case 1 and 2. And if either of the vertices that you labeled has an incident non-critical edge attached to it, you would label that edge and its other incident vertice, which by extension would also be non-critical, as n plus 1, which in this case would be 3. And from that point forward, if that vertice or the other labeled vertice, pretty much at any labeled vertice has an incident non-critical edge, you would label that pair as n plus 1, which is 4 and 5, etc., until there are no longer any non-critical edges incident with labeled vertices. Step 2 is where it branches out, because from this point the Betty number can either increase or decrease based on what the user wants. So if we wanted to increase the Betty number, i.e. increase the number of components the graph has, you would go to step 3. If you wanted to decrease it, you would go to step 4, and if all points were now labeled, which at this point is impossible, you would exit the output. So I'll start with step 3. And that looks like a lot, but actually step 3 is pretty much identical to step 1. The only real difference is that you would only necessarily pick one critical vertex and then label all of its incident non-critical pairs. And then if you want to increase it again, if you repeat step 3, and if you didn't, then you would return to step 2. And then if you wanted to decrease the number, you would go to step 4, which is very simple. Simply pick a critical edge that exists between any two labeled vertices, and simply fill it in with the next highest number, n plus 1. Now I understand that that's a lot to take in, so I'm going to walk you through an example. This is a gradient vector field with the critical and non-critical points labeled, and at the top is our desired homological sequence. So I'm going to number this one at a time, starting with step 1, labeling 2 critical vertices and all incident non-critical pairs. So we started with that vertex and that vertex, 1 and 2, and from there we labeled each pair that was incident with either of them one at a time, and in this case it brought us up to 7. And from there we want to decrease it, we want to go back to 1, so we would go to step 4 and label that critical vertex in between 2 and 3 as 8, because that's the next highest number. And now we're going to want to increase the Betty number 2 times in a row. So we would repeat step 3 twice with the only 2 remaining unlabeled critical edges and critical vertices and all their non-critical pairs. And you may notice in this case, we started with one vertex, labeled all its non-critical pairs, and then labeled the other vertex. That's the only other difference between step 3 and step 1. It's a very subtle difference, but I felt like it was still worth pointing out. And lastly, repeat step 4 2 more times, and we're done. So any questions?
Question or two at the heart?
I don't need to be the guy who asks about the applications. That's out there. Are there any apparent applications of this?
Well, the main idea behind our research was sort of just intellectual curiosity. I think in many cases, graphs and discrete Morse functions can be used for data analysis and possibly, did you say, what was it, robotic scanning or something like that?
Robot motion planning.
Yes, robot motion planning. There isn't any direct application from this, but we were hoping that building on top of that, we could eventually get to such a point, but for now, we would say yes, it's mostly just intellectual curiosity. JP, did you have a question?
Yeah. Have you expanded this algorithm to multiple dimensions, or have you just been working in graphs?
Yes, I should have said that. For this point, we were mostly just focusing on trees, which basically meant there were no closed surfaces. There are no 3-dimensional edges. There are just 2-dimensional edges. So in this case, no, this algorithm exclusively applies for